All right, guys, this is the start of the graph sketching section. We've done tons so far with concavity and increasing and decreasing and max and mins, and this is where we kind of put all of that together into our biggest application of derivatives so far. So based on first and second derivative, we know the first derivative tells us whether a function is increasing or decreasing, and the second derivative tells us whether a function is concave up or concave down. And so combining those, increasing, decreasing, concave up, and concave down, there's four combinations of those things that we can come up with. So we call those the four basic shapes that a curve can take on. So say, for instance, that the first derivative is positive and the second derivative is positive. That would mean the graph would be increasing and concave up. And so that would look like this. Increasing and concave up. It's increasing, we know what that looks like, and it bends upward like a concave up graph. So that is a positive shape. Positive first derivative, positive second derivative. Let's say that the first derivative is positive, but the second derivative is negative. That would mean the shape would be increasing and concave down. And that would look like this. And so that is positive first derivative, negative second derivative. The third of the four shapes, let's say now, because we've already used both the second derivative being positive, so let's switch the first derivative to being negative. So say the first derivative is negative and the second derivative is positive. That would mean our graph is decreasing and concave up. That would look like this. So decreasing and concave up. Negative first derivative, positive second derivative. And then our last combination would be negative, negative. Negative first derivative, negative second derivative. That would be decreasing and concave down, which would look like that. So that is negative, negative. So those are our four basic shapes. So it brings us to our big definition here, which is transition points. And we're going to talk about transition points a lot during this section. So when we're sketching these functions, we want to know when the graph is going to change shape. And we have these four basic shapes. So we can change back and forth. We could go from being, increasing and concave down to being decreasing and concave down. Or we could go from increasing and concave down to increasing and concave up. We can change shapes, and there are lots of different ways that we could do that. They change shapes at the transition points. So the transition points are points where the basic shape of the graph changes. Because f prime or f double prime changed. Let's say changed sign, just to be super specific. Okay, so if f prime changed sign, your basic shape is going to change. If f double prime changed sign, your basic shape is going to change. They could both change. So at any point where either one of them changes sign, we're going to have what we call a transition point, and at that point, the basic shape of the graph will change. So we're going to start with polynomials because, like I said here, they're the simplest to sketch. And so we've got a three-step process that we're going to follow. So step one, we want to come up with these signs. We're going to find the transition points. So find the transition points. And determine the signs of f prime and f double prime between them. So we set up a sign chart using these transition points, and then we see how the sign changes. And when we find out how the sign changes, we'll find out how the shape changes. Okay, and then quick step here, pay attention. Note that means you must find the critical points. That's where the first derivative is equal to 0 or undefined. You must also find the possible inflection points. That's where the second derivative is equal to 0 or undefined. And remember, we only call them possible inflection points because we need to actually look at the sign chart before we figure out if it actually is an inflection point or not. Okay, step two. Note what the transition points are and the sign combinations. And that will make more sense once we actually look at an example. Okay, so we're going to figure out what the transition points are, and so we've got at this next step, we want to sub in the x-coordinates, because in this step we'll have the x-coordinates of the transition points, but we want their y-coordinates so that we can be really accurate on our graph. So we figure out exactly where the transition points are, x-coordinate and y-coordinate, and then the sign combinations, like is it positive positive like this, is it negative positive like this, and that way we're getting closer to figure out what the basic shape of the graph is. So at this point, what we've set up so far is exactly where the transition points are, so we've probably plotted those on our graph, and then we know the sign combinations, and that's going to help us come up with the basic shape, and then we can draw the shape. So draw arcs of appropriate shape connecting the points. And then I probably could have put this before, but while you're plotting all of these points, the transition points, x and y intercepts are also a super convenient thing to have on your graph. All right, so here are all of the things that you will eventually use. This is a nice list to have. You need to know when your function is increasing or decreasing, when it's concave up or concave down, the local extrema, that's your maxes and mins, and their y values, which we find in this step. Inflection points and their y values, which again we find in this step. Asymptotes, if there are any, we don't get there yet with polynomials, but you will with rational functions, and then x and y intercepts. All right, so this is a really nice list to hang on to when you're doing these graphs, just to make sure that you've covered everything. All right, so we are going to look at this first example, and we're going to break this down like piece by piece. All right, so this is the only one where I'll write out this much information. If you see on the next ones, I really only have the equation, and that's because, we'll know exactly what we're supposed to be doing by then. So when we look at the first one, first thing we do is we take the first derivative. So like I said, I am really just kind of laying this all out there for you, baby stepping you towards this graph. So the first derivative, here's our original function. So the first derivative, y prime equals derivative of x cubed is 3x squared, and the derivative of negative 3x is a negative 3, derivative of 5 is just 0. So that is your first derivative. Next step, critical points. So while we're on our way to finding critical points, you might as well get the first derivative kind of as simplified down as possible. So we're going to factor out a 3, and then we can factor that down even further. So we know that's the difference of squares. Factors to x plus 1, x minus 1. You can take that step here, you can take that step here, either way, because critical points, what we're going to be doing is setting the first derivative equal to 0. So when we set this equal to 0, the critical points that we come up with are plus or minus 1. We get a negative 1 here and a positive 1 here, and that's by setting the first derivative equal to 0. Remember, in the future with rational functions, we also want to set the derivative, find where the derivative is undefined. That doesn't happen here. That's never an issue with polynomials, so we only look for where it's equal to 0. But again, in the future, you also need to find critical points wherever the function, the derivative, is undefined. Okay, second derivative. We go right back up here to our first derivative, and then take the derivative of that. So the derivative of 3x squared is 6x, and the derivative of negative 3 just goes to 0. So that's our second derivative right there. Any potential inflection points. Remember, we call them potential inflection points because we haven't checked a sign chart yet. For any potential inflection points, we're going to set the second derivative equal to 0, and that only happens at x equals 0. Okay, so our transition points. Our transition points, we want to actually find where those points are, and that's at -1, 0, and +1. So we're going to set up a double sign chart. I have told you guys before to get in the habit of labeling your sign charts, because in the future we are going to have double sign charts, and we do. So we're going to have a sign chart for y prime, and we're going to have a sign chart for y double prime. We're going to use every single one of the transition points to split up the sign chart. Make sure that they are in numerical order. So first we have the -1, then the 0, and then the +1. Okay, so we're going to use all of those points. Now pay attention to where each derivative might change. Like here, the critical points are plus and minus 1, so we know that the y prime is not going to change at 0. And then the possible inflection point is only at 0, so we know it's not going to change here. So we can keep that in mind when we're setting up our sign chart. So we're going to take some sample values. I'm going to make sure the derivatives are on the screen here so we can plug those in. So for y prime might change at -1, and it might change at +1. So we're going to plug in, we have 3 different sections here for the y prime. So plug in something less than -1, something like, a -2 or a -10. If I want to go big. So say I plug in a negative 10. If I plug that in here, negative 10 squared is 100. So this is definitely something positive. I come up with 297 if I plug in a negative 10. So the first derivative will definitely be positive. That means my function will be increasing on that little range. And then here for y prime, it's not going to change at 0 because that's a possible inflection point, not a critical point. So I can just plug in one thing in this region right here, and I might as well plug in 0. So if I plug in 0 to the first derivative, I get something negative. So I'm just going to put it in my two places just because I have a divider line here. And then something bigger than 1. Again, I can use something as big as 10. If I plug 10 in here, I get something positive. So here's what happens. Both of my critical points did end up being extrema. My critical point of negative 1 ended up being a maximum because my first derivative changed just from positive to negative, and then 1 ended up being a minimum because my derivative changed from negative to positive. Okay, so now on to the sign of y double prime. That'll check for concavity and inflection points. So 0 is the only dividing line here, so I only need to plug in one thing to the left and one thing to the right. So I could plug in anything negative. If I plug in anything negative here, this comes out negative. And if I plug in anything positive here, this second derivative will come out positive. So my graph is concave down to the left of 0 and concave up to the right of 0. That's what the sign of f double prime tells us. Okay, so I am going to combine all of that information to get my basic shapes. So note the basic shapes that we're looking on here. Positive, negative means increasing in concave down, decreasing in concave down, decreasing in concave up, increasing in concave up. We've got 4 different shapes. All 4 of them are represented here. So these transition points are where my basic shape will change. Okay, so local mins. Local mins are based off of y prime. You get a local min anytime the first derivative changes from negative to positive. So that happens at x equals 1. And now since I want to plot it, I want to know what the actual value is. I plug this into my original function because I want to know what the y value is because I'm trying to draw a graph of this function. So y equals, and I plug in 1, so 1 cubed minus 3 times 1 plus 5. So I've got 1 minus 3 plus 5, which gives me 3. So the actual coordinate point for my local min is 1, 3. So I will be able to plot that in just a moment when I start setting this graph up. Okay, next, local max. That is going to happen right here. If I look at my first derivative again, here I have a change from positive to negative, and so I know that's going to be a local max. Same thing as up above, I want to plug that negative 1 in. I always plug it into the original when I'm looking for coordinate points. Okay, so I have a negative 1 and a positive 3 and a positive 5, so that gives me 7. So the actual point that I will plot here is a negative 1, 7. Next, inflection points. Inflection point is a change in concavity, and so that is when the second derivative changes sign. That happens right here at 0. I go from a negative second derivative to a positive second derivative. So x equals 0 is my only inflection point, and again, I need to know what the actual coordinate point is. And so I plug that into my function. I plug in 0 cubed minus 3 times 0 plus 5, which of course comes out to be 5. So this is one coordinate point that I have. Okay, so my intercepts. My y-intercept, I literally just found that with my inflection point. It is 0, 5, and we only get one y-intercept, so I don't need to check for any other ones. The x-intercept, if I have this function right here, it's literally impossible to factor and solve x cubed by hand. You just can't do it. We could use a calculator, but that would kind of defeat the purpose because I could just plug the graph into my calculator to get all of this stuff. So this one is not factorable. Okay, so for my x-intercepts, my graph is not factorable. Now, this is not something, I don't want you to just look at it and be like, it's not worth it, I can't factor it, it's impossible. If it's factorable, like if it's a quadratic or if it's something trig related that you actually can plug 0 in for y and solve for x, then you should do it. But this one I am telling you that you can't. Okay, so we have all of this information. The next thing we do is we plot these points. We've got a big coordinate system here. So I've got 3 points that I can plot. This one is the same as this one. So I've got the point 1, 3. I've got the point negative 1, 7. So 3, 4, 5, 6, 7. And then I have the point 0, 5. Okay, so for all we know, without all this information, that would be like a perfect linear function. I could connect those dots and it would just look like a linear function. But if I look at the sines, this is the last step that I wrote down right here. Draw arcs of appropriate shape connecting the points. And so I know what shapes I'm supposed to have. So between, well, I guess negative infinity and negative 1, my graph will be increasing and concave down. So you can start with that. So start with a shape that is increasing and concave down, like that, until I get to that point. And then from 0 to 1, my graph will be decreasing and concave down. So you can kind of round this out here and come down to that point. Then after that, just from 0 to 1, my graph will still be decreasing, but now it'll be concave up. So we have a change in concavity here. So it goes like that. That's now concave up. And then from 1 on, we will be increasing and concave up. So that's a local min. I switch to increasing, and it will look something like that. So that is a pretty accurate view of my graph. I got my maxes, my mins, my inflection points. I know when it's increasing or decreasing. If it were quadratic or something easily solvable, I would be able to know exactly where this x-intercept was too. But that is a pretty darn accurate view of our graph. All right, so we're going to look at one more. I want to do, we did the one polynomial, so I want to do the sine graph here. So this one we're going to do all of the same steps. We're going to set up our double sine chart. So we start by finding the first derivative. And so the derivative of sine is cosine. The derivative of cosine is negative sine. Okay, so we set that equal to 0. And so when we set that equal to 0, it's the same thing as setting cosine equal to sine. So we should know our unit circle well enough to know when cosine is equal to sine. And that happens in the pi over 4 family, in the first quadrant, and in the third quadrant. So that is pi over 4 and 5 pi over 4. These are your critical points. All right, so our critical points are these 2 points right here. Okay, and then next will come the possible inflection points. So I take my second derivative. So take the derivative of this. Derivative of cosine is negative sine, minus the derivative of sine is cosine. So to find my potential inflection points, I will set that equal to 0. And so that's the same as setting negative sine equal to positive cosine. So what that means is we want sine and cosine to have the same values but opposite signs. And so that again happens with the pi over 4 family, but it happens in the second quadrant, 3 pi over 4, and then again in the fourth quadrant, 7 pi over 4. So there, one of them is positive root 2 over 2, and one of them is negative root 2 over 2. All right, and those are your possible inflection points. We say possible because the sign may or may not change. We're not sure. All right, so over here, I'm going to sneak in a double sine chart. Okay, so this is for y prime. This is for y double prime. We are blocked on the ends by 0 and 2 pi. All right, and then we've got 4 more pieces here to fill in. So pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Okay, so our signs might change anywhere in there, but pay attention to where each derivative might change. Like y prime, we don't need to plug something into every single one of these boxes. Y prime might change here and here. So I only have to plug in something here, here, and here. So be careful with that. So we're going to do a little work plugging some of these things in here. Might be something to do kind of on the side. Maybe I'll use this blank space up here. So for y prime, let's say I plug in a test value right here. So y prime, something smaller than pi over 4. The only thing we've ever talked about is pi over 6. So y prime, I'm going to test pi over 6. Okay, so when I plug that in, I plug it into my first derivative. So the cosine of pi over 6 minus the sine of pi over 6. Okay, so if you guys remember your unit circle hand trick, remember a little hand trick? So pi over 6 is right here. Cosine of pi over 6 is root 3 over 2. Sine is 1/2. So root 3 over 2 minus 1/2. We don't need to know what it is. We just need to know that it's positive. Okay, and then the next time it could change is 5 pi over 4. So I can plug something in between here. A really good one to use would be pi. Okay, so cosine of pi minus sine of pi. Cosine of pi is -1 minus sine of pi, which is 0. So that comes out to be negative. So that whole chunk is negative because I'm not going to change my first derivative at 3 pi over 4. And then something beyond there. So anything up until 2 pi. So we could do like 3 pi over 2 would be a nice easy one. Okay, so the cosine of 3 pi over 2 minus the sine of 3 pi over 2. So cosine of 3 pi over 2 is 0, minus the sine of 3 pi over 2 is negative 1. So that comes out positive. So we've got some extrema there, some sign changes on the first derivative. Okay, and then next we're going to plug some of these values into the second derivative. Again, remember the second derivative only changes here and here. So I've got 3 pieces on my sign chart. Okay, so let's sneak some work in over here. Y double prime, something between 0 and 3 pi over 4. I would go pi over 2. Use your nice easy ones. Use like the quarter marks if you can. So pi over 2 would be a good one. Here's our derivative that we're plugging that into. So negative sine of pi over 2 would be a negative 1 minus cosine of pi over 2 is 0. So that comes out to be negative. Then something between 3 pi over 4 and 7 pi over 4, I would again use pi. Okay, so negative sine of pi is 0 minus cosine of pi is negative 1. So that comes out positive. And then something between 7 pi over 4 and 2 pi, unfortunately, the only thing available to us is 11 pi over 12. I'm sorry, 11 pi over 6. Sorry, 6. 11 pi over 6. Okay, so 11 pi over 6. Unit circle, hand trick. We are in the fourth quadrant. So negative sine would be negative, and then when we're in the fourth quadrant, sine is a negative 1/2. So this ends up being a negative 1/2, which is a positive 1/2, and then minus cosine. So again, when we're in the fourth quadrant, cosine is positive root 3 over 2. So since this one's bigger, this ends up being negative overall. Okay, so that is our beautiful sign chart that we've got so far. We are going to find the actual minimum and maximum values. So we want to find any extrema we've got, any inflection points we've got. So we're going to find the min. We'll start there. The min, let's look at our sign chart. We got one right here, 5 pi over 4. So I'm going to plug 5 pi over 4 into my function right here. So 5 pi over 4, if I wanted to plug that in, I would plug in 5 pi over 4 to cosine, and so we might want to do, again, a little side work. So the original function right here is where I'm plugging these values in. So 5 pi over 4. Sine of 5 pi over 4 is a negative root 2 over 2. Cosine of pi over 4 is a negative root 2 over 2. So when I combine those up, I actually just get a negative root 2. So that is this y value right here, negative root 2. That is my minimum value. Maximum value, if I look at my y prime sign chart, I get one right here at pi over 4. So if I plug into the original function, sine of pi over 4 is root 2 over 2 plus root 2 over 2. That gives me root 2. Okay, inflection points. Inflection points happen when the second derivative changes. That happens here and here. So I have one at 3 pi over 4, and I've got another one at 7 pi over 4. Okay, so if I plug in 3 pi over 4, sine of 3 pi over 4 is root 2 over 2. Cosine of 3 pi over 4 is negative root 2 over 2. So they actually cancel and I get 0. And then the same thing happens when I plug in 7 pi over 4. I get a negative root 2 over 2 plus a positive root 2 over 2. So I get 0. So those are the coordinate points that I have so far. For my y-intercepts, if I plug in 0, I get, these are my two x-intercepts, I already just found those. My y-intercept, if I plug in 0 for x, sine of 0 plus cosine of 0 is 0 plus 1. So there's my one and only y-intercept. So now I'm going to plot all those points. Okay, so here's the 2 pi. So I can kind of cut everything in half from there. So here's pi, pi over 2, pi over 4, 3 pi over 4. Here's 3 pi over 2, 5 pi over 4, 7 pi over 4. Okay, so let's space this out a little bit. So let's say this is 1, and this is negative 1. And then root 2 is about 1.4, so we could put that like here. Positive root 2 and negative root 2. Okay, so those are just points that I need to plot that I have over here. All right, so I have a point 5 pi over 4, negative root 2. pi over 4 positive root 2, 3 pi over 4 0, inflection point, 7 pi over 4 0 is an inflection point, and then I have this y-intercept, so I might as well start there. Okay, so from 0 to pi over 4, I am increasing in concave down, then I switch to decreasing in concave down, so I can do that. So increasing in concave down, there's my max, switch to decreasing in concave down, whoops. This is an inflection point, so now I am changing to decreasing in concave up. Here's my min, now I am increasing in concave up, and then here's a point of inflection again, and so now I start increasing while being concave down. All right, so our graph is going to look something like that. All right, that's it.